benchmarks for audio reasoning, but our is so far the best one because it has the most complicated reasoning and it have a really what we call deep steps reasoning. And the reasoning assumption or the concept is really popular. It has been widely used in the natural language process community and also in the CV and the reasoning capabilities. And here is one example of our proposed benchmark. And on the left-hand side, those are some traditional audio reasoning or understanding benchmark. For example, what is the most difficult word in the tongue twist to be pronounced, or what is the relation of the two speakers? But in our benchmark,
Get out the table. Is he faking it? I don't know. Wait, come on. Oh hell! Nah, hell nah.
So the model will only be given the audios, and they will not see the subtitles or the video or the visual information of the videos. In order to understand these audio clips, you need to do the ASR, the automatic speech recognitions for both English and Chinese, and it also need to do the sound event detection to know it's probably inside a barber shop, so that some kind of objective will be relevant to describe the haircut. And it will also know the tones and also some specific words like what the hell or something like that, the meaning. So you have to understand all of them in order to answer these questions. So typically we need at least 3 reasoning steps to answer each of the questions inside our benchmark. And all of the questions, we have 1,000 questions. They are categorized into 4 different categories based on which attribute of the audio we should understand in order to answer the questions. Those 4 categories are the signal level, the perception and cognition level, the semantic level, and the culture level. For example, for the signal level, the model will be given on the audios of 3 different pitch pronounced by a ruler, and ask what is the sound for the longest ruler or something like that. In order to answer this type of question, the model needs to use some kind of signal processing algorithms to recognize the pitch informations or the rhythm information inside the audios. So we call this signal level reasoning. And for the second, which is perceptions or the cognitions, I throw a stone in a wheel, and maybe 2 minutes later, 2 seconds later or 5 seconds later, I hear the echo back from the bottom of the wheel. I need to use some kind of perception to know how many seconds between I throw the stone and I listen to the echoes or something like that. And then I need to do the calculations based on some cognition information. So that is in the cognition and perception level. And the third one is what is he and she refer to in some specific conversations, some really complicated conversations or something like that. So that's regarded as some kind of semantics level. And the last level is what we call cultural level, which we need to not only understand the music or some other audios, but also have some kind of knowledge for the audio memes or the music cultures. For example, the audio may show 2 melodies, one composed by John Strauss, and like bong sa sa da da da, another composed by Joseph Strauss. And the question is, what is the relation between the 2 musicians that compose these 2 different melodies? And the answer should be John is the father of the Joseph. So the model have to equip some kind of music domain knowledge or some audio meme domain knowledge in order to answer such questions. So such kind of reasoning is really hard for some large audio models to understand. And here is the portion of all type of the modality and all type of the levels that we have. In terms of the modality, we have the speech, audio, and music, and the mix of any of the 2, and the mix of the whole 3. And you can see everything that's relevant to speech has a really large portion, But we also have a really decent portion of the music and the general audios, and also the mixtures of them. So, and compared to the previous audio reasoning benchmarks, our task has the most difficult, what we call the deep steps for the reasonings compared to all the previous ones. And also all of the audios in our benchmark is derived from the recent YouTube audio links. So all of the audios are not included in any of previous video dataset or any of the previous audio datasets. So that is our contributions. And here I would like to show some kind of a result of the models. And we have 5 different types of models. One is the audio large language model. The second one is what we call the reasoning audio language models, which have some kind of like reinforcement from tuning or something like that. And the third one is omni modality, which have the capability to take visual and audio as input, and it typically also have a really decent reasoning capabilities. And we also use some kind of audio transcription and audio captions that connect with single modality large language models and large reasoning language models in order to fix such kind of problems. And the takeaway is, if maybe it's easier to see the result in this map. And here is the p-value map. The x-axis is the accuracy, and the y-axis is the p-value if the model capability is better than random guess is due to some model capability or not. And you can see all of the large audio model, open source large audio models are all below or not significantly past compared to the random guess. And the omni modality model, which can take 3 modality, is typically have a better capability compared to the large audio model, because during training it not only includes the audio perception data, but also includes many video reasoning data or the image reasoning data. So it can actually have a really good zero-shot capability on the audio reasoning. And what else? And we can also see here the gray column is the random guess, because some of the questions only have 2 choices or 3 choices. So the random guess is now 25%. And you can see for the semantic type, the question have a most decent accuracy, because the question is the most similar to the training set, like what is the conversation talking about or something like that. But for the signal levels, it is focused more on the audio perception and the music perception. The performance is generally the worst. And if you take the noise as the input, then most of the models, the noise input will be really similar, the performance will be similar to the random guess. But if you take the audio as the input, the result is pretty decent. So that is also show our benchmark have a really low language bias on the questions, on the choices. And that is show the difficulty of our benchmark compared to the previous one. And also the error analysis. The error is typically consists of 3 parts. One is the misunderstanding for audio perception. The second one is for the reasoning. The last one is lack of knowledge. And there are also some kind of errors that leads by the instruction following errors. So, and here is the code. And welcome to check our papers during the New Year's conference.
1 minute to the questions. Okay, so I will ask a question. So, in this kind of reasoning models for all modalities, like, do you have any solution to mitigate the bias of the language, like how to make the model really focus on other modalities instead of language?
Oh, okay, so how to reduce the language bias? Yeah. Okay, there are typically 2 methods. One method is you can pick up 2 two choices, and you treat both of them are some kind of correct choices, and you create the language bias. For example, one is A, another is B, and the third choice is not A but B, or not B but A, or something like that. You can try to use that kind of strategy to reduce the language bias, which is I think there are some kind of papers in Europe this year talking about these issues. Another thing is trying to create multiple choices and to only pick up those choices with the least perplexity or something like that. Those are all of the choices. If it have a really low perplexity, then the large language model is typically to choose because it have a more language bias, although it's a wrong choices. So.
Yeah, but in order to have like the multi-choice questions, you have to give the multi-choice questions, which means that you need some human input.
I mean, you can ask another large language model to generate the wrong choices based on the question and the correct choices, and you pick up the maybe 2 or 3 which have the highest or the lowest perplexity, or the probability is the closest to the correct choices or something like that.
And you have prior for the other language model that you used.
Yeah. Okay. Oh, go ahead.
I think most people in this room are doing multimodality on vision or multimodal alignment, derivation, and maybe text. So you're doing a little bit different to your audio. So what's the key difference you think is to make the different modality alignment when you're addressing audio compared with addressing alignment between text and video or visual information?
That's a really good question. Technically, the encoder is obviously the most different part. Like we replace the image encoder to an audio encoder. But from another perspective, audio has some kind of temporal informations. So it's more, from my perspective, like audio understanding task instead of the video, the image understanding task. From the technology perspective, yeah.
Okay. Let's thank